So yesterday, we started talking about Newton's universal law of gravitation. Okay, and that says that the force of gravity acting on an object, okay, can be calculated by taking our gravitational constant, multiplying the two masses that are attracted to each other, and dividing by the separation distance squared. All right, so what we learned from that is that certainly the size of the two masses influences how much gravitational attraction there is, okay, and how far apart they are exponentially affects how much gravitational attraction there is. Okay? Now, where that leads us to is a bit of satellite motion stuff, which we did yesterday. We did the speed of the moon as it orbits the Earth, okay, but also a little bit of net force stuff. All right, so kind of recall from Unit 2, okay? Net force, how do I calculate it? There was two ways. The vector sum of all forces. That's the most important way for us right now, okay? So if I'm looking at this situation right here, okay, where we have a lunar eclipse. So during a lunar eclipse, the sun and the moon and the Earth are aligned in the same plane as shown here, okay? So that means that the Earth moves between the sun and the moon. This is when you get like the blood moon, the moon that looks like really red, okay? Because as the light from the sun goes through the Earth's atmosphere, its wavelength gets changed a little bit, okay? And so it appears that the moon looks really red, okay? And you can see the shadow of the Earth eventually cast across the moon, okay? What we want to find out is what is the net force acting on the Earth in this orientation. So they're in a perfect line. Okay, what are the two forces right now acting on the Earth?
The gravity from the sun and the gravity from the moon.
Right, but we want to be careful about how we say that. You're right, yes, but not so much in the saying gravity from the sun, gravity between Earth and sun, and gravity between Earth and moon. Because the Earth is attracted to both. Right? Which one is it more attracted to? The sun. Okay? Right? It's like that whole Romeo and Juliet thing. Right? Rise, sun, rise, fair sun, and kill the envious moon. I'm not just a science guy. Okay. I'm not going to go any further than that because I don't remember the rest of that soliloquy. Something about her light is but sick and green, but none but fools do wear it. Something like that. Anyway, just to impress you a little. I know you're not impressed, but that's okay. Okay, so we got the Earth and the moon here. Okay, what we want to find is what's the net gravitational force acting on the Earth. This is one of the things that we're going to use to calculate that. So I'm going to give you guys a few minutes and see if you can find the net force due to the sun and moon, okay, acting on the Earth. All right, you have all the information you need right here in this chart. You have the mass of the Earth, mass of the moon, mass of the sun, and the distances between their centers. Okay, remember, net force is the vector sum of all forces. Okay, give you a few minutes on that one. All right, net force is the vector sum of all forces. Everybody okay with that? Okay, so if I'm looking at this from the Earth's perspective, okay, the two forces acting on the Earth are the force of gravity between the sun and the Earth and the force of gravity between the moon and the Earth. All right, do I have a way to calculate those two forces?
Yeah.
Yes. All right, so all I have to do is say that F net equals, okay, big G times the mass of the Earth times the mass of the sun divided by the radius between the sun and the Earth squared. And I'm going to add that to, but it'll be negative, so I'll just say subtract, okay, because that's quicker. Subtract big G times the mass of the Earth times the mass of the moon divided by the radius between the moon and the Earth squared. All right, I just have to calculate those two forces and subtract them, and I will have the net force of gravity acting on the Earth when the moon, Earth, and sun are aligned in this way. Okay, so what I'll be looking at then is this. F net equals, big brackets here, 6.67 times 10 to the minus 11 times 5.98, or sorry, they have 9.7. 5.97 times 10 to the 24, okay, times 1.99 times 10 to the 30. That's the mass of the sun. Okay, divided by 1.50. I think that's what they have as well, right? Yeah, times 10 to the 11 squared minus 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24 times 7 point, what do they have, 7.34? 7.35 times 10 to the 22, that's the mass of the moon, divided by 3.84 times 10 to the 8 squared. Okay, I perform that operation and I'm going to get the net gravitational force acting on the Earth. Whoops, 5.97. Okay, so the net gravitational force acting on the Earth, okay, is 3.50 times 10 to the 22 newtons. Is net force a vector quantity? Which way is this? Last semester, I went over that example and put it on the unit exam. That example. I didn't change anything. I just put it directly on the unit exam. People crapped the bed on that question. Okay? I don't know why. You don't even have to manipulate anything in that question. You just have to understand what net force is, and people forgot. Don't forget what net force is. It's kind of important. Okay? It's the vector sum of all forces. Everyone follow what we did there? Okay. Then, I want you to try it when the Earth, Moon, and Sun are in this orientation. Okay? So now, the Earth is out here, and the Moon is between it and the Sun. So I want the net gravitational force on the Earth in this situation. If you didn't erase all of your numbers, you can do this really quickly in your calculator. Okay? You can save yourself a whole bunch of time if you kept everything in your calculator and didn't erase it all. Okay, are we ready to go over that one?
No.
We're not?
Yeah.
Why not? We should be done already. What's the only thing we need to change on this question from the last one?
Negative.
Right, we just have to add them instead of subtract them. Now both the Moon and the Sun are pulling the Earth towards the Sun. Okay, so all we have to do, we already have the force of gravity between the Moon and the Earth. We already have the force of gravity between the Sun and the Earth. Those numbers don't change. All that changes is now the Moon is pulling in the same direction as the Sun, so we add them together instead. Okay, so if I just go to my calculator, I take my entry here from before, and I just go up and change that minus sign to a plus, and I'm done. Okay? That's all I have to do. Now it's 3.54 times 10 to the 22 newtons towards the Sun, or towards the Moon, whichever. They're both in the same direction. You could write either one and the vector would be right. Okay?
Wouldn't there be a force between the Sun and the Moon that would also pull it?
Well, but it's asking about the Earth. Yes, there is a force of gravity between the Sun and the Moon, but in this case it doesn't play a part.
Oh, wouldn't it, because the Moon's pulling the Earth, so if the Sun's pulling the Moon, the Moon would also pull the Earth?
That's why we're adding them together.
Yes. Okay.
Right? You're saying the same thing I'm saying, you're just seeing it from a different perspective. So the answer is yes, you're right. The Sun is pulling on the Moon, and that's part of why we add those two forces together. Okay? Yes, there is a force pulling on the Moon. It's not moving the Moon towards the Sun. okay? It's making the moon move in a circle around the Earth. Okay? And I mean, yes, in a more complex situation, if we were to analyze all the little idiosyncrasies of this, in this situation, yes, the moon would be pulled away from the Earth a little bit. Okay? Every time the moon goes to this position, it pulls a little bit further away from the Earth because it's pulled towards the sun. But remember, R is exponential in this equation, right? So the force of gravity, okay, is big G times mass over R squared. The moon is so much closer to the Earth than it is to the sun that it's way more attracted to the Earth. Okay? So that's why it doesn't fly off towards the sun when it's between us and the sun. Yeah? Okay. All right. Try number 2. This one may have to involve a little bit of trigonometry, because now the moon's over here. Okay? So now it's pulling the Earth this direction, 90 degrees to this one. You might have to draw one of those tail to head diagrams. Okay? All right, give you a couple minutes on that one. Okay? Because as I was just saying, this doesn't involve a lot of new calculations. You've already calculated the 2 forces that are involved in this question. So here's what we need. Okay? We've got like a free body diagram of the Earth. So here's the Earth. The Earth is being pulled this way by the force of gravity between the moon and the Earth. It's being pulled this way by the force of gravity between the sun and the Earth. And obviously this force is way bigger than the other. That's why the Earth orbits the sun and not the moon. Okay? It's just that much more massive. So if these are my 2 forces and they're both vector quantities, to find the vector sum of them, I would draw them like this. Force of gravity between the sun and the Earth, force of gravity between the moon and the Earth. Okay, I draw them tail to head. That means that the net force acting on the Earth is angled slightly away from the sun due to the position of the moon. All right, so the Earth isn't pulled directly towards the sun now because it's being pulled a little bit to the left by the moon in that particular position. So I just need to find F net, which would be the hypotenuse of this triangle, and then find the angle using trigonometry. All right, so once again, I can take the entry I already have in my calculator, and I just need to alter it slightly. So I'm going to get my entry in there, and I'm just going to go back here, okay, and I'm going to put in one more set of brackets. Actually, no, I'm not going to put in another set of brackets. I'm going to put in a square root sign. Okay, and then I'm going to drop down here. Put a squared in there and another bracket. Oh no. Plus. Okay, and then another. No, I don't need another one there. Yes, I do. Bracket. Oops. Not that kind of bracket. That kind of bracket. And another squared here. And I think I have the wrong number of brackets. I do. Shoot. I need one more bracket up here. See, this is why you shouldn't do it the way I just did it. No, I didn't do it. Anyway, I don't want to have to type in all those numbers again. But, okay, if we put in the force of gravity between the sun and the Earth squared, okay, force of gravity between the moon and the Earth squared, and then square root that, okay, after we add them together, we'll get our net force here, okay, which will be 3.52 times 10 to the 22 newtons, and the angle of deflection is only 0.3 degrees, which we can get using any trig function. Okay. We can use tan, or we can use sine or cos, whichever, because we'd have all 3 sides of the triangle, right? So you can see that the moon, even though it's way closer to the Earth than the sun is, still doesn't make a whole lot of difference because it's so much smaller, okay, than the sun. The sun's effect is much greater. All right, questions on that? Okay. Okay, so we already know that gravity can be an attractive force between two objects, and that gravitational force is affected by the mass of the two objects and how far apart their centers are. Okay? We also know that gravity can act as a centripetal force, and it's because of this that things orbit each other. Right? It's the reason why the moon orbits the Earth orbits the sun, and so on and so on. Okay? Anything that orbits something else is technically termed a satellite. Okay? There's natural satellites, and there are artificial satellites, at least around Earth. Okay? And a few other planets too. Okay? But natural satellites are things that are generally considered to be moons. Okay? And artificial satellites are those little things we launch into orbits. So, things we need to understand. Satellites obey the laws of uniform circular motion. That means that their speed in orbit does not change. It is constant. Okay? Obviously, the velocity changes because they're moving in a circle. Okay? The direction's always changing, but we're back to uniform circular motion. This is not a vertical circle. Okay? It's a horizontal circle, or uniform. Okay? The other thing we need to understand is that for all orbiting bodies, the gravitational attraction between the two bodies provides the centripetal force. In other words, always Fg equals Fc, but not this. Why not?
Because that's Earth's gravity.
Okay, because that's Earth's gravity, and that only applies if I know what little g is, and that's little g is only 9.81 if I'm on the Earth's surface. Okay, in orbit around the Earth, can that number be different?
Yes.
Yes. That's why instead of this, we're now talking about this. Okay? Gravity provides the centripetal force, but I have to calculate gravity using the big G, not the little g. Okay? Everybody follow me on that? All right, now, there's 3 m's in this equation. But 2 of them are the same. So which mass is on both sides?
Smaller.
The smaller one. Yeah. The orbiting mass is on both sides, which means if I do any manipulating, what will happen to it?
It'll cancel.
It'll cancel. Why will it cancel? Okay, mathematically, yes. I mean, like physically, why does it cancel? Why does it not matter? Does mass matter in a perfect physical world, as in terms of how fast something accelerates gravitationally? No. Okay, near the Earth's surface, everything falls at 9.81 meters per second squared. That doesn't change. All things fall at the same rate, regardless of their mass. Okay, so it doesn't matter whether I have a very small satellite or a very big satellite. Okay, they will need to move at the same rate or have the same orbital period, regardless. The only thing that affects them is what they're orbiting and how far they are away. Okay, the mass of the satellite actually doesn't matter. Okay. Now, the other thing we got to learn is essentially the premise behind getting something to orbit something else. And that is, the key to getting something to orbit is that it has to go fast enough that the distance it falls towards the thing it's orbiting is accounted for by how much that thing curves away. Okay? Because the Earth is round and not flat, okay, I need to make sure that as something moves in orbit, okay, the distance that it falls is equal to the distance the Earth curves away in that time. That way, every second it falls but never gets any closer to the Earth. Well, but apparently gets further away over on the left. But, okay, stays in orbit. Right? That's the key. And as far back as Newton figured that out. Okay? Now, he never made it work, but by that point in his career, everybody just took everything he said as truth. Okay? He actually stopped doing real experiments. He started doing thought experiments, which means he thought crap up in his mind and just said, hey, if I did an experiment like this, I can't. But if I did, these would be the results. Here you go. Okay? And people went, well, you're Newton. Okay. That's what he started doing near the end.
Did Isaac Newton make calculus?
Possibly. I don't know. I try to not remember much about calculus. Yeah, like who invented or anything else, or like its existence. Okay, so here was Newton's thought experiment. He said he could make a cannonball orbit the Earth if he took it to the top of a very tall mountain and shot it fast enough that as it fell towards the Earth, in the first second any object falls near the Earth's surface, it'll fall 4.9 meters. Okay? Now, in order for it to not get any closer to the Earth and continue to orbit the Earth, it has to go far enough that the Earth's curvature is 4.9 meters. That's 8 kilometers. Okay? So near the Earth's surface, something would have to travel at 8 kilometers per second in order to achieve orbit. Now, what's the problem with that? Well, not gravity, air resistance. You can't make something travel through the Earth's atmosphere near its surface at 8 kilometers per second. That's why meteors burn up when they hit the Earth's atmosphere. Okay? They're moving really fast, and there's a lot of friction. Okay? Like the fastest things that we built to fly through the atmosphere, like the SR-71 Blackbird, things like that can travel at like Mach 3, 3 times the speed of sound. When they land, you can't get out of them. They have to be cooled off, or you'll burn yourself when you get out. Okay? So we can't make anything go that fast within the Earth's atmosphere. But if we can get outside the Earth's atmosphere, we're a little bit higher, we don't have to go as fast, and we don't have air resistance as an issue. Right? So getting something to orbit the Earth requires us to get it essentially out of the atmosphere and moving pretty fast. That was a bit of a problem early on. Okay? Who did it first?
The Russians.
The Russians. Yeah. The Soviets were the first country to get a satellite to orbit the Earth. It was called Sputnik. It was like a basketball with 4 antennas coming off of it, and it orbited the Earth and went beep, beep, beep. Terrified people. Like people in the United States, especially people who were in like the Defense Department, were freaking out, man. Okay? Because if they could put something in orbit, then they could make a nuclear bomb drop anywhere they wanted on Earth because, well, it was orbiting the Earth. This is how people thought during the Cold War. Okay? If the Soviets could make something orbit the Earth, they could drop bombs from space. And they're exactly right. That's how an intercontinental ballistic missile works. Okay? You essentially launch it into low Earth orbit and then deorbit it over your target. Okay? And then it falls down and blows up. So you can understand why they would have been kind of intimidated by that. Okay? But really, all the satellite did was go beep, 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 and the Russians sat back in Russia and went, terrified Americans. Okay. But yeah, they made this thing orbit the Earth by making it go fast enough that the distance it fell was accounted for by the distance the Earth curved away. Now, it didn't stay in orbit forever, but it orbited, I can't remember how many orbits before it came down. All right, everyone understand that principle? So really, all a projectile is then, all a satellite is a projectile. Okay? It's just that its projectile arc connects and makes a big circle. Right? So if I don't make something go fast enough, this was Newton's idea, by the way. Okay? If I don't make something go fast enough, then it'll fall in a projectile arc and encounter the Earth, like this. If I make it go a little faster, it travels a little farther, just like all projectiles. Okay? Make it a little faster, it goes a little farther. If I make it go fast enough, that projectile arc just becomes a circle. Now, if you're Newton and this is a cannon, fire the cannon and get off the mountain. Because it'll come back. It'll go all the way around the Earth and come back and hit you. Okay? If it works that way. Obviously it doesn't because it was within the Earth's atmosphere. Okay? But he was theoretically correct on how that would work. Right? This is also then why on the International Space Station everything is apparently weightless. If you're falling, you feel weightless. Okay, that's why that flying in the vertical circle thing works. Okay, when we saw that video of the zero gravity trainer, okay, all they're doing is falling, and while they're falling, okay, everybody feels weightless. Okay. So a satellite in orbit is always the same height above the Earth, and it moves with uniform circular motion. Okay, so we can say that the force of gravity provides our centripetal force, just like this. Okay. If we want to solve for velocity, okay, then we just manipulate. We bring r over, and as we already talked about, the mass of the satellite will cancel because all things would fall at the same rate.
How many artificial satellites are there?
Hundreds, maybe even thousands at this point, lots. Okay, yeah. In fact, they have to be very careful when they're launching anything now. Okay, if they want it to leave Earth orbit, like if it's a probe going somewhere, they have to make it so that it doesn't hit anything. Okay, I mean, there's still a lot of empty space out there, but still, you don't want to hit something, right? Okay, now, another thing that can come up here has to do with substitution. Okay? We've said that for any satellite, FC equals FG. What if the question asks you or gives you the period of the orbit and not the speed? Right, then we have to do this. We've done this actually before. We talked about it earlier in the unit. Remember that V equals 2 pi r over t?
Yeah.
Can I substitute that in for V? As long as I do what to all of it? Square. Right, so if I'm going to do that, okay, so I'm going to have 2 squared, pi squared, r squared, t squared. Okay, if I have r squared on the top and r on the bottom, r on the bottom goes away, squared goes away on the top, right? And I'm left with this, m 4 pi squared times r over t squared. Okay, you're going to have to do that sometimes if you're asked to solve for period, or if you're only given period and asked to solve for radius or something like that. Okay, then you'll have to substitute that formula in. Okay, now I would caution you against writing this formula down, because obviously on unit exam, you're not going to get this. You're going to have to substitute this yourself. Okay, so make sure you understand how to do what I just did, which is take this formula here, square it, and plug it in. Okay, that's all I did, nothing fancy. Okay, so what I just talked about, that's what this slide is about here. If we want to find the period of a satellite's orbit, okay, then we have to plug in and find what t equals. Okay, and we can do that with that substitution. Okay, and obviously the further away from the Earth, the greater the orbital period. Everybody all right with that? Okay, what is the period of a geosynchronous satellite? One Earth
Rotation.
day, exactly. Okay, so some of you are going, what? I don't know. Okay, a geosynchronous satellite is a satellite that stays over the same point on the Earth's surface all the time. Okay, so these satellites out here, okay, so this satellite would always be over this spot on Earth. In order for it to always stay over that spot on Earth, it has to orbit at the same rate the Earth turns. Okay, so if it's going to do that, then it has to have the same orbital period as the Earth's rotation. Okay, now, most of our satellites are geosynchronous. We want them to be that way because what do we use them for?
Radio.
Radio, communications. Okay, so if you got satellite TV at home, your satellite dish doesn't move. It just always points upwards. Okay, and that's because the satellites it's communicating with are always in the same spot. Okay, it didn't always used to be that way. Right, way back in the dawn of satellite TV, satellite dishes were really, really big, and they were motorized. Okay, so they would track a satellite as it moved through the sky. So as you were watching TV, your satellite dish would move periodically and track the satellite. Okay, and then when it goes over the horizon, what does your satellite dish have to do?
Find another one.
Right, it's got to go back and find the next one coming over the horizon. Okay, that would always happen during double overtime. Okay, of Stanley Cup playoffs. Okay, that's when the satellite would go over the horizon, and then you'd be without signal for 2 minutes while your satellite just slowly rotated back. Okay, trying to find the next satellite in orbit. So obviously that was not good. Okay, having geosynchronous satellites is much better. Okay, we also want to have geosynchronous satellites because we want to look at the same places. If it's a weather satellite, okay, and it's telling me about weather here in Alberta, I want it over Alberta all the time. I don't want it looking at Albania. Okay, that doesn't help me. Right? I want it to stay over Alberta and track storms and weather and stuff like that in this area. Okay, not somewhere else. So most of our satellites are geosynchronous, okay? Including our GPS satellites, okay? The ones that help us with directions and location and stuff, okay? They're also in geosynchronous orbit. So a lot more of the traffic is out at this altitude. They all have to be at the same altitude to be geosynchronous. Okay? So there's a lot of satellites at that radius. Okay? Polar orbits are a lot smaller, okay? And we would use those for like special scientific satellites or spy satellites. Okay? If you're running a spy satellite, you don't want it sitting over the same spot all the time because it's an easy target. Okay? And yes, countries shoot down other countries' satellites. Okay? If you know somebody's spying on you with a satellite, you shoot it down. Okay? Or at least they used to.
Would it, like, on the cellular GPS, not satellite?
Yeah, but I mean the cell towers still use the GPS satellites to help them with that information. Yeah. Okay. Yes. Your phone's GPS is not using the global positioning system per se. It's bouncing a signal off of cell towers, right? If you're out of cell range, right, then usually your positioning is a lot less accurate. Okay. If you have a real GPS unit, then that's actually using a satellite.
As a satellite they shot it?
No, it's just using satellite signals. Those satellites are pushing heavy radio signals back down. So it's pinging off of several satellites. Okay, if you have one. If you've ever seen what that looks like, if anyone has one of those older units, okay, it'll tell you how many satellites it's locked onto. Okay, when they're locked onto 3 or 4, it's going to be accurate to within a couple of meters of your position on the Earth's surface. If it's only reading 1 or 2, then it's going to be less. Okay. Now, things to remember here. Orbital velocity and orbital period are independent of the mass of the satellite. Okay, and we already looked at the mass of the satellite cancels whenever we do any calculating, okay, because all things fall at the same rate if they're the same distance from the Earth. Okay. So, we'll go over a couple of examples here. We did the orbital speed of the moon yesterday, so we'll skip that one. Okay, Neptune's average orbital radius is 4.50 times 10 to the 12 meters from the sun. Okay, and Neptune is obviously a satellite of the sun. Okay, the mass of the sun is 1.99 times 10 to the 30. What's Neptune's orbital speed? All right, so start it out like this, and see if you can calculate the orbital speed of Neptune. Okay, using that. I'll give you a couple minutes. All right, so we're going to start out with this, okay? Gravity, the force of gravity between Neptune and the sun is what's providing the centripetal force, okay? So I'm going to say here, the mass of Neptune times the speed of Neptune squared over r equals big G times the mass of Neptune times the mass of the sun over the radius between Neptune and the sun squared. All right, so I'm trying to solve for the speed of Neptune, so I'm looking for V. So I'm going to multiply both sides by r. That r will cancel off the square. Okay? I'm going to divide both sides by the mass of Neptune. That will cancel. And then I will take the square root. So V will equal the square root of 6.67 times 10 to the minus 11 times the mass of the sun, 1.99 times 10 to the 30, divided by the orbital radius of Neptune, 4.5 times 10 to the 12. Okay, when we do that, we should end up with 5.43 times 10 to the 3 meters per second. Right? That means almost 5.5 kilometers per second. Okay, is the rate at which Neptune moves. That said, it still takes over 100 years for Neptune to orbit the sun. Okay, because it's so very, very far away. Okay? It has to travel a very, very long way. All right, how many people are on to number 2? Okay, before you do number 2, interesting fact. There is a naming scheme for all the moons in the solar system. Okay? Oddly enough. Okay? See, if you have more than one moon, you don't know what to call it. Right? On Earth, we're lucky. We only have one moon, so we call it the moon. Easy. Okay? But if you have more than one moon, then it becomes more confusing. You can't go, there's the moon, because there's another one over there. Okay? So, you have to have a naming scheme for all of them. And there is. Here's how it goes. Mercury has no moons, no naming scheme. Venus, no moons, no naming scheme. Okay? Earth, Earth is Terra, okay, and then the moon is Luna, okay. For Mars, Mars is the god of war. The companions of war are its two moons. The companions of war are fear and panic. Phobos, fear. Deimos, panic. Okay? I know that's weird. Okay, Jupiter. Jupiter is named for Zeus, who was the leader of all the gods. Jupiter has over 60 moons. All of Jupiter's moons are named for the lovers of Zeus. Yeah, well, not all of them were willing. Okay, Zeus was not a nice person. Okay, yeah. So just keep that in mind. Okay, but yeah, all of the moons of Jupiter are the lovers of Zeus. So yeah, and there's over 60, and we're not out of names yet. Okay, Saturn. Okay, Saturn's moons are all named after the Titans from Greek mythology. Okay, so Enceladus and things like that. So they're all named after the Titans. For Uranus, again, that's how you pronounce it. Okay, all of its moons are named after Shakespearean characters. Okay, so Miranda, I think, is from The Tempest. Okay, and then you've got like Puck and things like that from Midsummer Night's Dream, and yeah, there's all this. Okay, Neptune, which is the god of the sea, all of the moons have some sort of like aquatic theme. Okay, Triton, its largest moon, is named for the weapon that Neptune carries, the trident. Okay, and then for Pluto, Pluto's the god of the underworld. So all of the moons around Pluto, and Pluto actually has many moons, okay, are themed from the underworld. So its biggest moon, Charon, is the boatman that takes you across the river Styx. It's not Karen, it's Charon. That's not how they spell it either. Okay, sorry. It's spelled like Sharon, but it's not. It's Charon. Okay? Charon's the person who takes you across the river Styx on the boat. Okay? They're the boatmen. That's why in Greek mythology they would always put coins on the eyes of the dead. That was to pay him. Okay? To take them across the river Styx to the netherworld. Okay. So there's actually a naming scheme for all the moons in the solar system. So if you discover a moon around another planet, you don't get to name it after yourself or whatever you want. You have to follow the naming scheme, unfortunately. Okay? Yeah. Astronomers have this weird power trip on that. Okay. All right. So try question number 2 about Uranus's moon, Miranda. Okay. It is orbiting at 6.68 times 10 to the 3 meters per second. Uranus has a mass of 8.68 times 10 to the 25 kilograms. You need to find the orbital radius of Miranda's orbit. Give you a few minutes on that one. Okay, so here's where we start this question. Miranda is orbiting Uranus because it is gravitationally attracted to it. So the centripetal force keeping it moving in an orbit is being provided by the force of gravity. So those two forces are equal. That means mv squared over r equals big G times m over r squared. Now, one of these is the mass of the moon, okay, of Miranda. That's a W, not an M.
Miranda.
Start that over again.
Karen,
Okay, so I've got to manipulate here because I'm looking for the radius. Okay, and radius squared is on the bottom here. I'm going to move it over to this side by multiplying both sides by it. That squared is going to cancel off the r on the bottom. The mass of Miranda is going to cancel, right? And then I'm going to bring v squared over by dividing it. So I'm going to have that the radius of the orbit, is big G times the mass of Uranus divided by the speed squared. Okay, that's what my end formula is going to look like. When I plug in my numbers, okay, 6.67 times 10 to the minus 11 times 8.68 times 10 to the 25. Okay, that's the mass of Uranus divided by the speed of Miranda in her orbit. That's 6.68 times 10 to the 3, but that number is squared. Right? So when I punch all that in, I should end up with an orbital radius of 1.30 times 10 to the 8 meters. Okay? Everybody with me there? So, thing to remember here. anytime something is orbiting something else, it is doing that because of gravity. Fc equals Fg for any satellite. Okay? Any satellite. Okay, I want you guys to see if, because this is a tricky one, see if you can solve this one. We're looking for the orbital speed and the orbital period. Okay? They're telling you the altitude of the satellite here. Okay? So that might be important.
It's in kilometers.
And it's in kilometers, yes.